Okay, so let's have a look at this one here. So we got this beam, some sort. We're treating it as rigid, and then it's suspended from these three bars. They're otherwise identical, so equal initial length, equal cross-sectional area, made of A3736 steel, and their cross-sectional area is 350 millimeters squared. So I want to figure out what the average stress is in each bar when it's loaded up. So let's redraw the situation here. Free body diagram. What we have here is we're going to have the beam itself will be subjected to the loads applied, and it will also be the two loads applied, the 50 and the 80, and then it's going to have some sort of reaction from those three wires. So I'll call that dy, ey, and gy. I replaced f with g because I don't like using f in the diagrams, because then you get ff and it confuses things and so on and so forth. Anyhow, yeah. So what we want to do is find out, first thing to do, find out kind of the relationship between those forces. So one thing we do know is that by Hooke's law, the force in each of the suspender bars is going to be proportional to the displacement. So when we pull down on these things, all the bars are going to move down at least somewhat. But since we don't have an equal loading situation, an even loading situation, we've got the 50 kilonewtons here, and we have the 80 kilonewtons on this side. That means that the side on the right here is going to move down further than the side on the left. So you're going to get some sort of rotation of the bar as well. So based upon this original position, you're going to get, so here's our original position, here's the final position. So you're going to get some amount of stretching in the bar AD, and then you're going to get, so that amount of stretching will happen in each of these bars. And then on the other two bars, you're also going to get an additional amount of stretching that is a function of the angle. So again, we're using the small angle approximation here so that we don't need to worry about which one's worry about the fact that this is the hypotenuse instead of the adjacent, so on and so forth. So based upon that approximation, the magnitude of the additional displacement is going to be the angle times the distance between here and here, and then here and here. So 2 meters times that angle for the bar in the middle, and then 4 meters times that angle for the bar on the right. And also known that this displacement is equal to in general, the displacement, the stretchings, the elongation there is going to be equal to the load times the length over the area times the Young's modulus. So if we're solving for the load, that's just going to be the displacement times AE over L. So all those bars, they got the same area, they've got the same Young's modulus, and they've got the same initial length. So we could solve for a general load in terms of its individual displacements. So throwing in the 45 millimeters squared and the 200 gigapascal, again I translated that to 200,000 newtons per millimeter squared. A gigapascal is a 1,000 megapascals, so 200,000 megapascals. A megapascal is a newton per millimeter squared. And then, of course, L, I just changed to millimeters, so it's 2,000 millimeters. So all that works out to 45,000 newtons per millimeter times delta. So the force, the reaction force dy, that's just going to be 45,000 newtons per millimeter times the delta d ad. The vertical reaction at E is going to be the 45,000 newtons per millimeter times that stretching plus that additional bit of stretching due to the angle. And then same deal for G, just based upon that displacement there. So all of them stretch by at least this amount, and these two stretch a bit further because of the angle. So we know what those forces are in terms of their displacement. We're still going to need to relate them better, so we just need to start using our equilibrium equation. So what I'm going to do is I'm going to take a moment about D. So taking about that point there. So let's just go from left to right. So we got the 50 kilonewton force acting over 1 meter. I'm going to put everything here in terms of newtons and millimeters, just to keep, I like to keep the unit systems consistent. And then next thing we got is EY. So first off, that's a negative minus. Sorry, the first one's negative. This one's positive. EY is acting upwards. So 45,000 newtons per millimeter times AD times the 2,000 millimeters times the times the angle, and then times the 2,000 millimeters for the distance between D and E. Then minus the 80 kilonewtons and the 3 meters between the D and the point of application of that force, and then just the one for GY. So that'll be 45,000 newtons per millimeter times the displacement of AD times 400 millimeters times the angle times another 400 millimeters for the distance from D to G. So just doing a bit of algebra, that works out to 290 times 10 to the 6 Newton millimeters is equal to 270 times 10 to the 6 newtons times delta AD plus 9 times 10 to the 11 Newton millimeters times the angle. So still got two unknowns there, still not quite able to resolve what's going on, so we need to use another equation to figure out what's going on. So I got the moment about G. So I'm going to do it from work from the other end. So that'll just be the that'll be our come on, let me erase. So we'll start out with our dy, and again, I just point out here again, dy. If we're taking the moment about G, dy is going to be negative, EY is going to be negative. The 50 and the 80 kilonewton ones will be positive moments. So yeah, I got the negative 45,000 newtons per millimeter times our delta AD times the 4,000 millimeters between G and D. Next up, we've got the 50 kilonewton force times the 3 meters between them. Next, we got E, so the again negative 45,000 newtons per millimeter times its displacement times its distance between G and E. And then next up, just the 80 kilonewton force times the 1 meter between them. And again, keeping everything in newtons and millimeters. So, just a bit of algebra again. 0 equals blah blah blah. So we end up getting 270 times 10 to the 6 newtons delta AD is equal to 230 times 10 to the 6 Newton millimeters minus 1.8 times 10 to the 3 Newton millimeters times the times the angle. So we got this value here, the 270 times 10 to the 6 Newton delta AD, and that term also ended up in this equation up here. So we can just take this and plug it into there. So that's what I'm doing here. So got the 290 times 10 to the 6 Newton millimeters from here, plus this from here, and then just the last term from here. That ends up giving, so the only unknowns there, the only unknown there is our angle. So we can just solve for that. It ends up being 8.33 repeating times 10 to the negative 5 radians. So now that we solved for our angle, we can go back and solve for our displacement. The displacement is the displacement at AD. So again, just reusing the equation that we had already used, 270 E times 10 to the 6 Newton delta AD is equal to 230 times 10 to the 6 Newton millimeters minus, and again we're just plugging in the value, minus 1.8 times 10 to the 11 Newton millimeters times what we found for our radius here. Sorry, not our radius, our angle. So 8.33 times 10 to the 5 radians. So relatively simple from there to solve for delta AD. Which gives us 0.796 millimeters. So the left, when we load this thing up, the left side here is drooping down 0.796 millimeters. And then from there, again, we can solve for the forces, the reaction forces, because we've got both of the unknowns there. We got the delta AD and we have the radius. Sorry, the angle. So doing so gives us 35.82 kilonewtons for dy, 43.32 kilonewtons for EY, and 50.82 kilonewtons for GY. And if you're wondering, that adds up to just to within rounding errors of 130, which is what we expect because our total force, because our forces applied are 50 kilonewtons and 80 kilonewtons. So at least that's consistent. And then once we got that, relatively straightforward to solve for our stress. Just this value here divided by our area, our cross-sectional area. So the cross-sectional area for each of the bars was 450 millimeters squared. So just take what you had here, divide by that, and it'll give you this. So again, I just translated that into newtons. So we're getting newtons over millimeters squared, which spits out MPa. So 79.6 MPa for the leftmost bar, 96.3 MPa megapascals for the middle bar, and 113 megapascals for the bar on the right. And that is about it.